We call it subduction when one plate descends into the mantle below another plate. The feature that results is known as a subduction zone. The oceanic lithosphere sinks below the continent as the rocks of the oceanic plate are more dense than those of the continents. Water-rich sediment rests on top of the ocean floor, and the minerals of the oceanic crust often contain water in their crystal structure.
Earthquakes occur as rocks in the descending plate fracture, and high pressures cause minerals to undergo changes in composition and crystal structure.
As the plate descends into the mantle, it is compressed and the water is squeezed out of the sediment and minerals. At a depth of approximately 100 kilometers, the water enters the much hotter mantle rocks immediately above the subduction zone. The addition of the water causes these mantle rocks to melt.
Melting generates magma that rises to the surface to form volcanoes.
Finally, the force of the collision produces mountains along the leading edge of the overriding plate.
Similar processes occur where two plates of oceanic lithosphere collide. One significant difference is that we no longer have a contrast in the composition of the converging plates. So, what determines which plate undergoes subduction? While each plate is composed of similar rocks, the rocks are often of different ages. Relatively young oceanic lithosphere is warmer and less dense than older lithosphere.
Consequently, when two oceanic plates converge, the plate with the older lithosphere undergoes subduction. We see this in the western Pacific Ocean, where the older Pacific plate is subducting below the Philippine plate that is composed of rocks more than 100 million years younger.
Just like in the ocean-continent convergence, earthquakes occur in the descending plate, and the rocks of the plate are compressed to squeeze out water, which enters the much hotter mantle rocks overlying the subduction zone and causes them to melt.
The principal difference is that magma rising to the surface now forms an island arc, rather than a volcanic arc, and there are no associated mountains. Otherwise, the processes are similar.
The third type of convergent boundary is represented by continent-continent collision. Before the two continents can collide, we have a typical ocean-continent boundary, but eventually the ocean basin is destroyed and the two continents converge. This is the process that occurred before the Indian subcontinent could collide with the rest of Eurasia about 10 million years ago.
Continental crust is too buoyant to descend into a subduction zone, so there is no source for magma generation and subsequent volcanism. Instead, the leading edge of each continent stacks up to produce unusually thick continental crust and results in higher elevations, similar to those observed in the Himalaya mountains today.
Finally, we'll leave you with some simple analogs for the characteristics of convergent plate boundaries. We can use some basic geogestures with the addition of some very geological oven mitts to model the processes of the three boundary types.